Hello, let's do another example, and we're going to extend the previous example, but we're going to look at a couple of other points because we want to find out what's going on at other areas on the beam. So here's the same beam as I had in the previous video. I have 125 newtons on the far right-hand side of the beam. I have a pin support at the far left side, that's at point A. And then at point B, at 8 meters from the left-hand side, I have a roller support. We determined that the roller support had an upward force of 156.25 newtons, and the pin support on the left-hand side had a downward force of 31.25 newtons. We've already found the internal forces at point Q. We did that in the previous video, but just to rehash that, we discovered that the shear force was upward, so V is 31.25 newtons. Technically, V is negative 31.25 because by convention, the shear force is down. And then the moment, which by convention is counterclockwise, in this case was clockwise at 125 Newton meters. And so technically, the moment was negative 125 Newton meters, if you go back to that previous video. But I've drawn it positive here. All right, so those have already been done. There are the equations, some of the forces in the Y, some of the moments about point A. I chose point A because it makes my life easier. There were no some of the forces in the X because there are no X forces in this problem, and that's going to oftentimes be the case. So what happens if I choose point R, which I designated R as being 6 meters from the left-hand side, from point A? So when I look at the diagram, I've got a moment and a shear force, and then there's still this 31.25 newtons over here, and it's downward. And so when I do the sum of the forces in the X, I'm going to get the exact same equation, the sum of the forces in the Y, I'm going to get this exact same equation that I had at point Q. That doesn't change. And so the shear force will be 31.25 newtons negative. This points down, so negative means it's pointing in the opposite direction, so it's pointing up. But when I do the moment equation here, it's a little different than it was when I did the moments at point Q. This time, minus V is going to be times 6 meters because it's 6 meters from point A, which is where I'm summing my moments, right? I'm summing the moments around point A, and then R. So there's 6 meters in here. And so my moment equation has to be altered slightly by putting 6 meters in here. Then plus m, because remember, the moment by convention is counterclockwise or positive. And so when I solve that out, I get the moment equals minus 187.5 Newton meters. So the important thing here is that the moment is different at Q than it is at R. So it's changing throughout the beam. All right, it's changing throughout the beam. And that's one of the things we're going to want to look at. We're going to want to look at how is the moment related to the position on the beam? How is the force related to the position on the beam? Well, speaking of which, let's take another point. Let's go to some point S. And S will be at 9 meters. Okay, so I've got the diagram started over here. I know there's 31.25 newtons pulling down at point A. I know there's 156.25 newtons pushing up at point B. There's 125 newtons over here at the far right-hand side, but notice my cut is at point S. And so that's really not part of this problem because it's off of the beam, at least as far as the cut is concerned. From here to here, it doesn't exist. So, or it's not affecting it, let me put it that way. So we're going to get rid of that. Just like we did not consider the 156.25 newtons for these two examples, because it's not on that cut. It's way over there to the right, right? So it's not on that left-hand cut that we're talking about. All right, so there's my forces. Then, again, by convention, I'm going to draw the shear force down here. Okay, so the shear force is down, and so I'm also going to have a moment, which I'll draw in there, and that moment is up, right? And so, that moment is counterclockwise, and so I've got that force in that moment. So now, what do I do here? So when I look at the sum of the forces in the y, again, there are no forces in the x direction, so we're not going to worry about that. I'm going to get minus 31.25 newtons down plus 156.25 newtons up, and then minus v, and that's going to equal 0. Right? That's going to equal 0. And so when I solve that out, I'm going to get that v equals minus 31.25, because that's negative. When I bring it to the right-hand side, it's going to be positive. Minus 31.25 plus 156, that's 125 newtons. So the shear force now is in fact down, but we consider down to be positive for shear forces, and so that's 125 newtons, right? Okay, so notice the equation is quite a bit different, not quite a bit, but it's different than it was over here. Okay, so the shear force V has a different value than it did for these first two examples at points Q and R. And that's because there's a change that takes place when I get to the other side. All right, and then when I do the sum of the moments, and again, I'm going to take the sum of the moments about A, no force there, so no moment rather, and then at B, I'm going to have 156.25 newtons, and that's at 8 meters. And then V is trying to go this direction, so that's going to be clockwise, so minus 125 newtons times 9 meters, because that's where V is, and then plus M is equal to 0. All right, so M will equal 125 newtons times 9 meters, because when I bring that to the other side, it's going to become positive. This is going to be negative, minus 156.25 newtons times 8 meters. Whatever that turns out to be, okay? And that will give me my value for M. I'm not going to finish that solution. You can do that on your calculator. All right, and that gives me the moment and the force at point S. Notice the moment equation, also a little bit more complicated. Here I only have V times the distance and then the moment, but here I've got one of the forces that's now come into play, and then V times the distance. So the equation has changed. And so the equation looks quite a bit different on the left side. The moment equation looks quite a bit different on the left side of V than it does on the right. And that's going to give us some piecewise functions. And that's something that we're going to have to look at in different scenarios. Okay? The other thing that I'm not going to do here, but if I did the right-hand side, okay, so this is still point S, then remember that there is now this 125 Newton force. Oops, that should be in blue. There's a 125 Newton force acting on that right-hand piece, right? The 156 isn't there because it's to the left of point S. And same thing with the 31.25, they're to the left of point S. But keep in mind, if I do that over here, V is up, and M becomes clockwise instead of counterclockwise. But if you do the sum of the forces and the sum of the moments on this, well, you can see already, when I do V, I'm going to get 125 newtons. Same. I get the same thing, right? I get the exact same thing. And then when I do M, I'll get the same thing that I got there. So either I can do from the left or I can do from the right. For me, I just like to be consistent and just continue doing it from the left, but you can do it however you so desire, and it will work out fine. All right, we'll take a look at a different example in another video. If you have any questions on this video, please leave them in the comments below. Thank you.